Mohamed, come on up and let's talk about University of Central Florida.
Okay, thank you, Ed. Jordan. University of Central Florida, I guess you figured out where it is. Following the Disney keynote speaker this morning, yes, we are very close to Mickey Mouse. So the university now is 68,000 students. So the latest I checked, it is the second largest in the nation after Arizona State. So it's a pretty large campus. So that transportation group is a very strong group. I personally have been there for 25 years now. I started the road safety program. I started to teach classes dedicated to road safety. I think this was one of the first in the country. So if you want to, check, you can Google. The latest I checked, all the databases like the Web of Science, Scopus, etc. You're going to find that this team is the most cited in road safety. So if you put road safety, traffic safety, safety analysis, any keywords, last 5 years, last 10 years, you're going to find we are the top cited in the world in this area. So we have contributed a lot to road safety, and the idea did not come only in the challenge. There are certain things that we did for the challenge, and for that I thank USDOT because it made us refine our thinking to meet the challenge. However, a lot of the algorithms that I will be showing have been developed over almost 15 years. And it started with me talking to the Florida DOT back in 2004 and saying, you're collecting all this data. At that time, we had loop detectors, right? Or, loop detectors with all their problems. I said, why are you collecting all this data? ITS data. We didn't even use the term big data at that time. And I said, they said, because, ITS and we need to estimate travel times, etc. And I said, did you think about safety? This refined data is being collected for freeways at that time, for every lane. Why, what are you doing with it? Give me a chance to look at safety. And started a series of projects at that time that we proved that this data is very useful for safety. Now we have much, much more data and more opportunities to use the data. Now, I want to tell you that, that the best time for me when I get approached by someone that read my papers and implemented this work. And I named two incidents 2 years ago in Korea. A Swedish person, a consultant, came to me and said, you have inspired us to use this model, which was a real-time safety model, on freeways in Stockholm, and we reduced crashes by 50%. And I have been in a team in Shanghai with my former students who are now professors at Tongji University, where we developed a system and a plan that led in 5 years to reduce about 40% of fatalities in Shanghai. But I have never implemented this close to home. And this is now my opportunity. USDOT gave me the opportunity to show you what we can do with all this work that have been implemented around the world. So I will start by showing you a video. I hope there is sound.
The first component is for traffic operators, which is password protected. Here is the user interface for operators. The left side window shows different groups of functions for real-time traffic safety management based on multi-source big data from vehicle detectors, connected vehicles, signal controllers, and weather stations. The first function displays the numbers of the high-risk locations in real time, which are identified based on deep learning algorithms developed by the UCF Smart and Safe Transportation team. The high-risk locations are classified into 5 categories for freeways and arterials. Also, the number of high severe crash risk locations is displayed, and the specific locations are visualized by the red jumping icons on the map. The list of the top 3 high-risk locations with the predicted crash risk scores are also provided. Take Freeway Basic Segment as an example. If operators click any of the 3 bars, the map will zoom to the selected high-risk segment. Meanwhile, the real-time crash risk, speed, and volume characteristics of the selected and its adjacent segments could be visualized in the right side window to assist operators to get a better idea about what is happening on the segment. Operators can also select segment directly from the map to get detailed information. Real-time CCTV images are also available for operators to check the field status. Additional data sources could be integrated into the system to conduct further diagnostics, such as videos from UAVs and surveillance cameras. For high-risk locations, proactive traffic management strategies are provided automatically in order to prevent and mitigate potential crashes in real time. These strategies are generated based on previous studies conducted by the UCF SST team, which have been extensively evaluated by simulation and field studies. For example, the system suggests the integrated variable speed limit and queue warning sign for this high-risk segment. To alleviate the crash risk, a queue warning sign is recommended at the end of the queue, and the speed limit of upstream segments should be reduced gradually. To augment the component for operators, the system accesses real-time data from 300 Lynx buses and 50 UCF shuttles. Based on each vehicle's trajectory, 3 types of critical driving events, hard brake, hard acceleration, and the high-speed standard deviation, are generated as safety indicators. The critical events are generated in real time and updated every 60 minutes. Also, more information of each vehicle can be obtained by clicking its own icon. In addition to the current bus or shuttle's data, the system has the capability to integrate other floating cars if data are available. Section 2. Decision Makers. Let's move on to the section for decision makers, which is also password protected. The first function shows the dynamic temporal status of the historical safety situation for multiple aspects, including crash frequency, crash risk, and different types of critical events from floating vehicles. The system can summarize the historical PATM recommendation at different time periods. Users can also download historical implementation reports to investigate road safety conditions and schedule their recurrent strategies proactively. For the high-risk locations without PATM devices, an installation recommendation could be provided. The historical events data are saved and displayed in the decision maker part. The crash diagnostics function is based on historical crashes. First, the decision maker can look at macro screening for crash analysis, which is at the zone level. Here, the zones are classified by zip code. Decision makers can check the crash frequency and rate by severity level, and they can see the map on the right side by clicking on the severity level. Meanwhile, decision makers can click each zip code area to see the severity distribution. With the same function, decision makers can also check the violation types. In addition, they can find at-fault drivers' residence. As a result, decision makers can target areas to educate for a particular violation. For example, if they want to reduce the DUI crashes caused by teenagers, decision makers can get the map of those teenagers' residence and overlay it with high schools to educate accordingly. At network level, we provide a decision safety support system. The system offers the most efficient countermeasures and their expected costs and benefits based on the Crash Modification Factors Clearinghouse. According to the recent 3 years crash data, the locations with the most potential for safety improvement are identified and highlighted with the red color. The decision maker can click any of the identified segments to check its suggested countermeasures, which are selected from 6,000 countermeasures for different crash types and facilities. For example, the Decision Safety Support System recommends 2 different countermeasures for this location. Their costs, benefits, and BC ratios are estimated respectively. Besides, for arterials, social media data, including Twitter and Strava, are added. Decision makers can see people's concern about pedestrian safety from Twitter. Meanwhile, Strava data shows bike activities to help improve bike facilities. The last component for decision makers is the CAV component for the county level. Safety improvement by CAV is estimated from our research. For example, if 25% of vehicles are CAVs, it is expected around an 8% crash reduction. Section 3. Public Users. Lastly, safety information is available for the public, and it can be accessed by any user. This information pertains to crashes related to pedestrians, cyclists, and violations in their zone. If users click a region, they can see the heat map and severity level. Also, bike lane information can be accessed by cyclists. Additionally, the real-time traffic condition is provided. The locations of schools and hospitals are included for the convenience of the public. The UCF SST team has been a traffic safety pioneer. We have spent over 20 years extensively researching crash occurrence factors and analyzing crash data from many states in the U.S. Based on these efforts, we have developed this visualization tool which uses real-time big data analytics, AI techniques, crowdsourced data analytics, and more. This tool will power road safety management with cutting-edge technologies and provide life-saving insights for each road user. Our system will play an important role in developing safer and smarter cities for the future.
All right, so this is an overview. There is not much, maybe it's not a lot of details, but I will try to give you some more details. So basically, what we are trying to do, by the way, this video is done by my students. Everything that we done here, we done in-house, myself and my students at different levels. Some of them have since graduated, and I have hired some of them with the hope to continue this type of work. So as we speak, we are trying to innovate new applications. The team is multidisciplinary. My students are not only civil engineers or transportation engineers, but we have also computer scientists and IT working, because I have a new degree in my department, master's in smart cities. This is the first degree in engineering in the country, by the way. So now we recruit not only civil engineers, but also other engineers and other people interested in smart cities. So they enroll in our department. So let me explain the concept again. So there are two major components. There is the public side, which is a little component, could grow. But the main components are the operator side and the decision maker side. These are two different. Of course, both can access both of them. But the operation side uses real-time data. So all the data that is available in real time is being fed into our lab. Of course, this is through agreements with the Florida Department of Transportation, the counties, the city of Orlando, etc. What we do is that we process this data in real time through our algorithms. The algorithms are mostly, so this is the data, and you can see I hope I can point. Okay, most of this data on the left side is the data that you are familiar with, which is, the crash data. Signal for Analytics is also crash data. The developer actually is Dr. Earlier sitting in the audience. The violation data that we get, highway safety motor vehicle, the CMF clearinghouse. The CMF clearinghouse is about 6,000 or more treatments for specific locations and conditions, etc. And by the way, if you check, you're gonna find about 500 of the estimated CMFs in the clearinghouse developed by us, and they are in the clearinghouse now. But we use the 6,000 CMFs. The roadway design characteristics from Florida DOT. We use the census data because we look also at the spatial side. But what is more important now is the right side, because this is the new types of data that we are using. So all the detectors for the infrastructure, such as the microwaves, the loop detectors, the AVIs, the Bluetooth detector, here data, which is something like Google data that we are getting also in real time, CCTV camera, etc. All this we are getting in real time. Now this is the signal data, Grid Smart and ATSPM. This is related to arterials that we are also getting in real time. So the signal data, as it changes, we are getting that. The number of vehicles and the signals, we are getting that. and different measures of the intersections we are also getting. In addition, so this is what we call infrastructure-based sensors. Now, we have connected our UCF shuttles, which are the small buses, as well as 300 of the transit buses to our system. So we are getting the trajectories in real time of these about 350 vehicles. Now the platform is there, so the next step is the police cars, the state cars, etc., will be connected. As long as it has a GPS, will be able to get the live data also. So the platform has been already built during this challenge. Now we have an app to get the real-time weather, because weather also play a role in safety, and we have the Twitter and the Strava data as crowdsourced and social media type data. Okay, so we talked about the traffic operator. So let me try to explain the concept. So the concept that we came up with many years ago is that if I know the conditions before crashes, so there is certain level of turbulence that happen that lead to crash. First, we proved that concept using about 5,000 crashes on I-4. I'm talking here about 15 years ago. Is if you look at historical crashes and you look at the time leading to historical crashes, 5 minutes before, 10 minutes before, 15 minutes before, can we classify this condition in real time? And the answer is yes. There is a certain level of turbulence or abnormal traffic that we drive, right? And we change lanes, we change our speed, we behave in a certain way. Our behavior affects the behavior of traffic. And we all drive, so you're driving speed limit, you're driving free flow, and there is a queue downstream. You don't know that, right? So as soon as the queue shock wave reaches your location, you are basically driving into a wall. If you are not gonna adapt your speed and respond accordingly, you will hit the back of the wall. We all face that. Like you're driving and then suddenly you find traffic backing up. This is one condition out of 7 real-end conditions. So over the years, we improved this. I can now tell you not only there's a crash, but I can tell you what type of crash. And different types of crashes depend on different type of data and different conditions leading to the crash. We can tell you if it's more likely to be severe or non-severe crashes. And then we took this into ramps, intersections, arterials, freeways, weaving sections. So we can now classify exactly based on the data. We can tell you exactly what you expect. Right? So this is what is meant when the video was showing the different risk. It's not risk actually, it's a measure of the probability or the likelihood of a crash and whether it's going to be severe or not severe. But we not only did that. When we looked at the time leading to the crash, we were able to estimate our algorithms 5 to 10 minutes or even 5 to 15 minutes before the crash happened. And the idea is to be able to intervene with ITS technology to reduce the risk in real time and prevent the crash from actually happening. If I know that in the next 5 minutes, this turbulence will lead to an inattentive driver or a driver that's not paying attention or a probability of a crash, I can intervene and reduce the risk by ITS measures. ITS measures could be queue warning, and this is what the Swedish did. I explained this before. Or variable speed limits, or control the ramps, or warnings, or at least I'll be ready to save the vehicle or reduce the severity of the crash. So we are developing predictive model. So all the colors that you saw is the expected risk after 5 to 10 minutes and not now. Because we want to be able to proactively, and this is the concept that I explained here, proactive traffic management. It's not enough to have active traffic management. It has to be proactive because we want to prevent crashes. So these are two concepts that we came up with over the years with maybe 6, 7 of my PhD students, is how we predict for different locations in advance and how we mitigate it in real time. These are the two concepts. This is what we took, and then we built this system. So everything that you see in the interface is built in the challenge. And we added the decision support system, what we call it, decision safety support system. We added AI so that the system could be seamless. It's working. And the operator just need to monitor what's going on. So this shows some of that screens, the visualization screens that I just showed. Why we are showing these parameters? Because we know from research that these parameters affect the probability of crashes. The standard deviation of speed, for example, is a measure of the turbulence of traffic. And therefore, if you reduce the turbulence, this is a surrogate safety, right, or an indication of crashes. So we are trying to reduce it in real time. Now, what's going in the background, and I don't want to spend time here, this is what's going in the background. So we have models for expressways, models for arterials, intersections and segments, freeways, weaving sections, ramp, regular sections, merge sections, etc. We are using a combination of statistical and machine learning or deep learning models simultaneously, and we are fusing the results in order to improve the accuracy. So not every model structure fit every location and every day. All this is fused in order to come up with the crash algorithms in a hybrid way, and this will give us an indication of the risk of crashes and the risk of severe crashes. This is what we are doing in the background. So these are some images of some of the output we are using. Also, this is actually was a little part when we submitted the challenge, but this is becoming a big part of our work now. And now this is the recommendation in real time, as you saw in the video, Q warning in addition to variable speed limit in order the vehicles to stabilize the flow approaching the location of the problem. This is being simulated and animated. So you can see some animation here. This is the coming from the floating cars, or what we like to call connected cars. Basically, you are getting the trajectories of the car. One of the important factors that we are getting from that is again the standard deviation of speed, which is again a measure. So there are infrastructure detectors, and these are vehicle-based detectors. And both of them are giving us an indication of the turbulence in real time.
We should probably wrap it up here.
Okay. So, the decision maker, basically what the decision maker is getting everything that has been coming from the real time part, but aggregated so that he can see the pattern. Okay, so we know that every morning at this location there is high risk, and we have said, Q warning at this location. So therefore, maybe the decision maker need to think that it should be a permanent solution to this location, other than the real-time, day-to-day that the operator is dealing with. Anyway, this is the different levels of data that we are using for decision making. The decision maker also is getting other measures such as the measures from the clearinghouse, etc. So the traditional safety approach and other safety approaches are all given to the decision maker so that he can see or she can see the full picture. There is a report of infrastructure changes that need to be done, as well as temporary changes that need to be done. So this is using AI. You saw in the video the violations, etc., and the macroscopic level. This is more for education, etc. These are the result of a network screening, and you can see the red parts which needs attention. And also the decision support system that's telling us what is the best solution for these locations. And then I think the public, we can skip quickly over this since I exceeded my time. The artificial intelligence that we are using in modeling as well as in suggesting the solutions. This is, needs some time to explain. We are also, the system has the ability also to adapt to new technology. In the video, we mentioned that our research have led to indications of how much CAV can reduce crashes. This is a very detailed analysis that we did based on all the available studies that looked into, and here we are looking mostly at ADAS, not really automated vehicles, right? I mean, what's in the market really is levels 1 and 2 and 3. So levels 1 and 2 and 3 are different technologies designed to reduce certain types of crashes. So if you match the percent of these vehicles in traffic and the systems that and which crashes they are designed for, you can track back and see which crashes you can reduce, and this is where we get the percentage of reduction as the market penetration of this technology increase. I thank you for your attention, and sorry, actually I didn't exceed my time.
That's okay. Yeah. Thank you.
Thank you very much.
Maybe we have time for one question there.